In this video, we're going to talk about graphical methods. And graphical methods can be used to help not only describe kinematics of a situation, but also describe the kinematics of more erratic motion or situations where you have possibly more complicated curves. Now, recall that we had the derivative of the position curve equals velocity. Well, what this is really saying, if we want to think about this, is that the slope of the S curve equals the value of the velocity at that point. So say I have some curve, some S versus T curve, and at some time 4, this equals, say, 16, because my curve here has the equation S of t equals t squared. It's a parabola shape. So if we take the derivative of this with respect to t, we end up with 2t. And at the value of 4, 2t is 2 times 4, or 8. And this is then the value of the velocity at that time. Say I take this value at 1, t equals 1, then the value of the velocity here is going to be equal to 2. Let's put this down here, 2. And now, since this relationship is a second order relationship, anytime we take a derivative of that, we're going to lose an order in our equation, and from a second order we would go to a first order equation or a line. Taking this idea to the next step, we can look at the derivative of the velocity with respect to time equals our acceleration. So then the slope of the velocity curve equals the value of the acceleration curve. So, of course, in this really simple demonstration, the derivative of 2t with respect to t then equals 2 at any point here. So that indicates then that the acceleration is constant for all t's, and constant at a value of 2. So notice the velocity curve is constant here. The acceleration curve is constant. The velocity curve is a linear curve, has a slope to it, and the position curve is one order higher than the velocity curve. So not only can you go in this direction and determine what your graphs look like, you can also go in the opposite direction with a similar idea. So note the change in velocity so say I look at my acceleration curve at a point of 1, we see here that the area here is 2 times 1, or 2. So the change in velocity between the initial point and 1 is 2. Now, if we take our initial velocity to be 0, if we look at the equation, that actually is the case. But the initial velocity could have been anything, but here in this situation it happens to be 0, then the change in velocity, v2 minus v1, equals the area of acceleration up to that point. So in our case, again, it's 0, so v minus 0 equals 2 times 1 equals 2. And in fact, that is actually the case. This is equal to 2. So we could then plot our next point by figuring out from this position where v equals 2, how does it change? Suppose we didn't know what our curve looked like up there. Well, the area under the curve. Now, this area that I'm going to shade pink here, this area is three times 2 equals 6 is the area under the curve, and 6 plus 2, so equals 8, and that will give us this point. Now again, we know if we have a constant acceleration, that when we do this move from the acceleration curve to the velocity curve, we're essentially integrating, so we're gaining an order of magnitude in the equation. So we go from a constant relationship to a linear relationship, and it has to be a linear relationship. So if we find 2 points, we can just sketch in the line, and we know that is good for the rest of the points in the relationship. And you can, of course, figure out another point here using this method to check your work. So, of course, the change in our position equals s2 minus s1 equals the integration of velocity. So the area under the velocity curve. So let's do the change in displacement equals the area under the velocity curve. So in this case, this is a triangular curve here that starts at 0 and ends at 4. So this is 4 times 8, or 32, divided by 2, or 16. And we see that at the same time up here, 4, our S-curve here has a value of 16 at that point. And we could do this for any point on this curve. And if we had multiple points, say we know this starts at here, and at 1, a value of 1, this would equal 1. We could sketch in this point. Then we could just draw a curve here that connects these points and label it a second order relationship. So why is this useful? Well, let's say that I'm given my acceleration here, and my acceleration curve looks something like this. So it's a piecewise curve with uniform acceleration or constant acceleration at different times. In one point, the acceleration is equal to 0. So when the time goes from 0 to 15 with this sort of acceleration profile, I can use the information that the velocity change is equal to the area under the curve at these times. So I can figure out then that my first point of velocity we know is going to be 0. Then my second point of velocity over here is going to be the area of this first box over here. So 1.25 times 4 equals 5. So let's put a value of 5 here. So at some position 4, the value of the velocity is here is 5. Then I recognize that this is constant, so this must be a line between these 2 points, so I can sketch in a line. Has to be a straight line. Okay, so now between point 4 and 10, or time 4 and 10, the acceleration is still constant here, but it's equal to 0. So if the area under the curve for acceleration is equal to 0, then there is no change in velocity, and that exists through this whole situation between 4 and 10. Let's go to 10. So this remains constant. So this first point, v2 minus v1, equals 4 times 1.25, like we said, with that equal to 0. The second region, we have our delta v equals, the total equals 0. So our change in v equals 0. So now we're here, and we want to figure out where we're going to go from there. So we now look over here at our curve, and we see that 5 times minus 1 is minus 5. So essentially what we've got going on then, that v2 minus v1, or again, since we're going to look at this region now, v2 minus v1 equals minus 5, or v2 equals minus 5 plus v1 equals minus 5 plus 5 equals 0. So v2, the point here, equals 0. Now, since this is a constant function over here, it means we gain an order 1, and since it's a negative value, the slope of this is negative. So now we've constructed our velocity curve. We can take that curve and construct our displacement curve. So we begin at 0. For our S1, we know that S2 minus S1 equals the area under our velocity curve. And S2 minus S1 equals 5 times 4 times 1/2, the area under this curve here. And looking here, we see that S1 is equal to 0, so our change is just 10, and I've got it plotted right here. So for our next relationship, then, 4 times 10 is 40 in this middle region. It's a square. That's the difference between S2 and S1, or the difference between this S, which is 40 up here, minus 10, or 30. So this is a point that's a value of 30 here. And you can calculate the difference in the results in the final point of 52.5. Now, one thing I want to mention before we end here is how we look at these curves. So the slope of the S curve equals the velocity at that time. So in our case, the velocity initially is 0, so the slope of this curve is 0. Then the slope increases as a second order function. When it hits this point, notice the slope of the V curve here is equal to 0, which means it will be a constant slope here. And then at this point, the slope starts going down, reducing until it hits 0 here. So we know the slope is 0 here, and the slope is higher here, and reduces is a second order function. And that's how we would sketch these results using graphical methods.